Krantz GmbH – Thermal Comfort. Here is your Krantz team, and in this presentation we will be looking at what makes an indoor environment comfortable and to which factors we should pay attention. We have all experienced bad thermal comfort and its consequences. Example includes sitting in very hot or very cold offices that are stuffy and give us the feeling of not being able to breathe properly. Working in factories amid dust and machine heat. Or even sitting comfortably in a theater while some parts of our bodies are freezing. It becomes more difficult to concentrate, our productivity diminishes, and sometimes we even get sick. Each building has a different purpose, and each therefore must be analyzed and designed according to its specific characteristics. We can control the internal environment through HVAC, heating, ventilation, air conditioning, which constitutes the technology and engineering specific to interior environmental comfort, especially in buildings and vehicles. These systems can range from a small air conditioning unit in a single small structure, for example, to huge multi-chiller systems and boilers for large buildings. The development of thermal comfort in Europe and the United States, together with the development of the idea of an interior climate, intensified at the turn of the 20th century. In the beginning, air condition often meant controlling the humidity of the air. Later, air conditioning technology spread to other buildings, such as offices, hotels and houses, where it was used to regulate both temperature and humidity. The control of the interior climate became the main objective, regardless of seasonal variations and surrounding climate conditions. Later, standards were created to help guide engineers in their designing of new systems and to help them keep both the environment and thermal comfort in mind. Technical standards are developed so that HVAC professionals have access to up-to-date procedures when testing, installing and designing equipment. With regard to thermal comfort in commercial buildings, Krantz follows the European standards. EN 15251 for indoor environmental input parameters for the design and assessment of energy performance of buildings. EN 13779 for ventilation of non-residential buildings, and EN ISO 7730 for ergonomics of the thermal environment. VDI 3804 office building air conditioning, and for industrial buildings VDI 3802. Krantz prepared a document with the layout specifications for thermal comfort based on the standards in order to assist professionals in the analysis of thermal comfort criteria. The feeling of well-being in an area depends on a number of specific external influencing factors such as indoor air temperature, radiation temperature, air speed and indoor relative humidity, and is defined as the condition of mind that expresses satisfaction with a thermal environment. The international standard ISO 7730 combines all these parameters in two indexes: predicted mean vote (PMV) and predicted percentage of dissatisfied (PPD). Predicted mean vote (PMV) is an index that predicts the mean value of the thermal sensation votes through self-reported perceptions of a large group of people on a sensation scale expressed from -3 to +3 and corresponding to the categories cold, cool, slightly cool, neutral, slightly warm, warm and hot. PMV calculations require the following inputs: metabolic rate, clothing insulation, air temperature, air velocity, mean radiant temperature, and relative humidity. Predicted percentage of dissatisfied, PPD, is an index that establishes a quantitative prediction of the percentage of thermally dissatisfied people determined from PMV. The main factors causing local discomfort or dissatisfaction may be the result of overly high indoor air velocities, Draught rating DR in percent, overly high vertical temperature gradients, too much radiant temperature asymmetry, and uncomfortable floor temperatures. Based on this study, this table provides us 3 different comfort categories, A, B, and C. The category to be fulfilled will be agreed upon between the consultant and the client and will serve as the basis of the HVAC concept. You will find all the following information detailed in our layout specifications for thermal comfort, as mentioned before. Thermal comfort criteria. When we consider what makes a room comfortable, we tend to think of temperature first. That's true, but there are other important factors to be considered, such as air temperature, thermal radiation, physical activity, clothing, air velocity, and humidity. Air temperature. The temperature of the room is one of the most noticeable factors in comfort. Independent of our activity or clothing, our body will try to maintain a temperature of around 37 degrees Celsius, and if our core body temperature deviates from this by even a few degrees, our bodies will begin to fail. So we need to be in a room not too hot and not too cold, and with a good air circulation. As a general rule, occupants will feel comfortable in a room temperature around 20 to 22 degrees Celsius or 68 to 72 degrees Fahrenheit. This can be influenced by the activity of the person and what the person are wearing. It is necessary to make clear, however, an important point. Temperature is not the same thing as thermal sensation. Thermal sensation, in turn, takes into account temperature, relative humidity, and airspeed. In the occupied zone, one should consider the interaction between air temperature and the radiant temperature of the enclosing surfaces, particularly when rooms are fitted with chilled ceilings or buildings have large glass facades. The local temperature, theta, is called the operative temperature and is determined from the average of the room air and mean radiant temperature. The operative temperature and the radiant temperature are also classified in relation to the 3 categories of thermal environment according to EN ISO 7730. In the left table, we can see the allowable operative temperature according to the 3 categories for thermal comfort, A, B, and C. In the right table, we can see the allowable radiant temperature asymmetries, likewise according to the classifications A, B, and C. For example, looking to the operative temperature table according to category A in summer, the ambient temperature should vary between 23.5 to 25.5 degrees Celsius, and in winter between 21 and 23 degrees Celsius. According to DIN EN ISO 7730, the asymmetry of radiation for the warm or cold ceiling is related to a horizontal surface element and for the warm or cold wall to a vertical surface element. With the assumption that only one thermally active component is in radiation exchange with a person, the mean radiation temperature is calculated for each of 2 fictitious half-rooms. The difference between these 2 mean radiation temperatures is the asymmetry of radiation. The value determined for the asymmetry of radiation is then compared with the values recommended in DIN EN ISO 7730, and thus the category A, B or C for thermal comfort is determined. With turbulent mixing ventilation and a chilled ceiling operating in cooling mode, the limits for vertical temperature gradients are of no significance, as the related values are always far below these limits. With displacement ventilation and a chilled ceiling operating in heating mode, however, one should take care that the limits for vertical temperature gradients are not exceeded. Also, the vertical temperature gradient and the surface temperature of the floor are important influencing factors for the thermal comfort, energy efficiency, and the selection of the optimal ventilation system. For example, the current standards recommend a temperature difference of up to 3 Kelvin per meter between the head and the feet of a person according to category B. The floor temperature can also cause discomfort and also interferes in the performance of the ventilation system. The following table shows the acceptable values for the surface temperature of the floor depending on the category of thermal comfort according to EN ISO 7730. These values are used as standards for commercial buildings, but the floor temperature needs also to be taken into account for other applications. One should note that the radiant temperature asymmetry is calculated using the surface temperatures of the enclosing walls, ceiling and floor and their angles of radiation. The latter depend on the location of the workplace. As a rule, it has to be checked whether the workplace nearest the facade complies with the criteria. The heating capacity of a chilled ceiling is restricted in order to satisfy the limit of the radiant temperature asymmetry. The graph on the right shows the radiant temperature asymmetry in the half rooms, ceiling, floor, as a function of the specific heating capacity in watt per square meter floor area. The illustration below shows exemplary the influence of the different room surface temperatures on the specific position of a sitting person at a height of 0.9 meter above the floor and at a distance of 1 meter to the facade. Thermal radiation. Thermal radiation is the heat transfer that happens due to electromagnetic waves that are emitted by a warm or cold surface. For example, sunlight in buildings is a great example of radiation. Here you can find two examples for thermal radiation: the heat transfer in a workplace and the use of special clothing for protection, and a thermal simulation showing heat radiation from panels on the ceiling and into an office space. We can improve or reduce the radiant temperature by basically putting a barrier up between us and the heat source. Whether it's a shade, a wall, or insulation, we just need to block the path of the thermal radiation. Here you can find 3 examples. A very common example used by architects to reduce thermal radiation, either cold or hot, through double-skin facade solutions. Wind blinds widely used in stores, shopping centers and large entrance halls, and an example using a curtain unit from Krantz FSG used to help insulate the windows and interior space from external radiation. Activity. How much energy our bodies will burn is mostly associated with our level of activity. For example, someone who sits down at a desk all day will consume far less energy and will feel cooler than someone who is constantly moving around all day. The more energy we consume, the more heat we need to reject. When designing work areas, it is important to take into account the activity and try to keep people of different activity levels separated within a building so that we can provide thermal comfort levels tailored to their needs. The presented table provides us the metabolic rates in Met and watts per square meter according to the daily activity. 1 Met is equivalent 58 watts per square meter. Those rates are important to calculate the total heat load in a specific space, remembering that sensible heat increases the room temperature, but latent heat can also increase the humidity. Clothing. Clothing can provide an insulation layer between the person and their environment and can affect their comfort. The following tables present basic thermal insulation values for typical outfits. You can find the complete table and also more information this regards in the standard EN ISO 7730. As an example, comfort limits for operating temperature are given in this graphic, depending on the level of activity and clothing. The arched areas indicate a comfort range around the optimum temperature. 0 klo corresponds to a naked person. 1 klo corresponds to the insulation value of clothing needed to maintain a person in comfort sitting at rest in a room at 21 Celsius or 70 Fahrenheit with air movement of 0.1 meter per second and humidity less than 50%. A typically person wearing a business suit. A person with thin clothing who is not performing physical activity will feel comfortable at a relatively high temperature around 26 degrees Celsius. A person with insulating clothing who is performing physical activity will feel comfortable at lower temperature levels around 14 to 18 degrees Celsius. Air velocity. Air velocity is another aspect which makes a big impact on a person's comfort levels. The faster the air moves, the greater the heat exchange will be. The fluctuations of airspeed, which are characterized by turbulence intensity, increases the sensation of draught and thus affect the thermal comfort. The graphics beside show us the maximum allowable indoor air velocities to meet the corresponding category A or B. Category A corresponds to DR equal 10%, DR draught rating, category B to 20%. For example, to achieve the category B by a temperature of 22 degrees Celsius and an air velocity from 0.2, we will have a turbulence intensity between 20% and 40%. These values are important for the choice of the different air distribution systems. It is important to note, for example, that for turbulent LFS1 reads at 40% and for displacement ventilation at 20% degree of turbulence. Therefore, higher air velocities are allowed for displacement ventilation. Allowable indoor air velocities in industrial plants are specified, for instance, in the German standard VDI 3802, air conditioning systems for factories, and also in the ISO 7730. In an industrial workplace, depending on the activity, it is often necessary to use special protective clothing. For this reason, the allowable mean indoor air velocity is also rated to activity levels and clothing, independent of turbulence intensity. As shown in the graphic, we can see the relationship clearly. For example, with a room temperature of 25 degrees Celsius, a metabolic rate of 2.0 Met, and a clothing factor of 0.9 klo, a mean air velocity of 0.38 meters per second is allowable. Humidity. When we talk about humidity, we mean the relative humidity, RH, which is the ratio between how much moisture the air contains and the maximum amount that the air could hold to a given temperature and pressure. Warmer air can hold more moisture. When you approach 100% humidity, the air moisture condenses. This is called the dew point. We can obtain this information from a psychrometric chart, see table. The psychrometric chart is an important tool for HVAC engineers to carry out heat load or cooling load calculations and to find solutions to various air conditioning-related problems. We will cover this in more detail in further presentations. We all know what an excess of moisture can cause in buildings, in cooling systems, especially in hot countries, and in air quality. The accumulation of fungus and bacteria, among other things. But how can a good air distribution system control or avoid such moisture? Taking into account infiltration areas like the entrance of buildings, open windows, the spaces between floors, where people accumulate, etc., it becomes necessary to be aware of the infiltration points. To use predictive control systems to control and prevent the accumulation of local humidity or even to increase the primary airflow rate to avoid condensation processes. Now that we have seen the importance and the main points to be observed for thermal comfort when designing an HVAC system, let's take a look at our laboratory where our equipment is developed and tested, in order to provide our customers with the best solutions for air distribution systems.